So we introduced weak topology in the last class, and today we'll see weak star topology. And there is a mistake in what I said last time, so which I am giving it to you as an assignment. I will give 2 more assignment problems. There is a correction in my. I said that I said the following: if you have a Hilbert space H is a Hilbert space. Then a sequence xn contained in X xn converges to X weakly is equivalent to saying xn en not xn en xn ek converges to x ek for all k where ek is y and b. We need one more condition. This is one condition. The second condition is this xn should be bounded, uniformly bounded. It's all this norm xn. Okay. So we need this condition. So we have to prove that if something converges weakly, then it is bounded. Then if it is bounded and if it converges, this weak convergence happens only for an orthonormal basis, then it is actually weak convergence. So the assignment problem is slightly slightly different. Yeah, someone asking something. So this is what I said, then this is the correction. You need one more condition. The second condition is needed. Okay. Yes. So you can take a Banach space also, dual space. That will be, it's the same thing. So let us work with Hilbert space. Is contained in H, be total. Total means you take the span of S and take the closure of the span, that is equal to S. That's what total means. Okay. Then a sequence xn contained in H, xn converges to X weakly, is equivalent to saying 1, xn is bounded, and 2, xn s converges to xs. These are all just number for all s and s. Okay. So it's enough to have the weak convergence, and when you have a uniformly bounded sequence, then it's enough to have the weak convergence over a total set. Okay, it's very easy to prove. We have already seen these kind of things. You have to use uniform bound. Of course, you have to use uniform boundedness for this way. If it converges weakly, then it is bounded. You have to use uniform boundedness. Okay, so that's the only thing. The other way is just some manipulation. You have to, using some epsilon and other thing, you will get it. Okay? If you use the usual epsilon by 2 trick or something, you will get it. Okay? I hope you are hearing me properly, because I don't have any interaction with anyone. Okay? Okay. So this is about weak topology, and we want to talk about weak star topology. So what is weak topology? Weak topology is on a Banach space X or any non-linear space. It is given by all the functions, all the linear functions. So the weak star topology is given by the pre-dual of that. Okay? So let X is a Banach space. Let us take Banach space. X star dual. Then weak star topology on X star is the topology given by all the evaluation functions, lambda x, x in x, where lambda x at phi equal to phi of x. Okay. So you take the, instead of, if you take all linear functions, this is the topology on X star. Okay. If you take all linear functionals on X star, which is X double star, then that is a weak topology. Okay. Instead, you take all the functionals given by the pre-dual. It's given by the evaluation function, okay, which is in the X double star. X is contained in X double star, and it is the topology given by that X. So this is what is called weak star topology. And of course, weak star topology and weak topology on a dual space coincides if the space is reflexive. It's clear. So it's a remark. If X is reflexive, that is X double star, it's isomorphic to X. I mean, it's not just isomorphic. I mean, it can be just it's not just some isomorphism where the isomorphism is given by this lambda X to X. Okay? So this map is an isomorphism, isometric isomorphism. This map is of course isometric. If it is an isomorphism, if it is onto, that's the only condition. If it is onto, then it is reflexive. And if it is reflexive, then weak and weak star topology coincides. Okay. So if it is not reflexive, whether it coincides is the question. So that is the another second assignment. I mean, I will tell you the proof orally. So, so to if you want to have the weak and weak star topology, we don't want them to coincide. Then we need to have non-reflexive spaces. So and the non-reflexive only non-reflexive space we have studied is L1, of course. So let X equal to C0. All sequences converging to 0. Then X star equal to L1 and X double star, which is L1 star equal to L infinity. Okay, so this we have seen. So then we want to prove that. I mean, we have already seen weak topology does not coincide with the norm topology by producing open ball. Here we can prove that. I mean, we can prove the other way also. Something converges in weak star, but it does not converge in weak topology. So that is an. I mean, certainly weak topology is bigger than weak star topology. Okay, clearly. I mean, we have more functions which that gives the topology for weak topology. So this is certainly contained in weak topology. So we only have to prove it's a strict when it's not reflexive. I mean, it's true when it's not reflexive. It's true in general, but we will see for this example because this is the only space we know. Okay. So then we have to consider something given by. So what do we do? Yeah, and it's enough to prove that you have some function and it is continuous with respect to weak star topology. It's continuous with respect to weak topology. No, if it is continuous with respect to smaller topology, it need not be continuous with respect to a bigger topology, right? Which is the other way. It's the other way, I think. Let me write it. So, if it is continuous with respect to smaller topology, then it converges in the bigger topology, then it's converges in the smaller topology. So I think it's the other way. What should be the right thing? So let us take this function. So we have to consider L1. L1 is the dual space where we have to consider weak topology and weak star topology. Okay, consider phi from L1. I mean something which is given by L infinity, a functional given by L infinity. Phi from L1 to C, where any sequence xn going to you can take the L1 functional 111 which is given by that, so which is summation xn. Okay. So this is assignment. This also is this is the assignment I'm giving you. So prove that this function is P is continuous with respect to weak topology not with respect to weak star topology. This is second assignment. Okay. Weak star topology is a smaller topology. If something is continuous with respect to, no, which way is that? If something continuous with respect to smaller topology, okay, if something converging continuous with respect to weak star topology, then something, so I have to write the other way, right? So if something is continuous with respect to weak star topology, then if something converges weakly, then that converges weak star, so the limit will also converge. So it should be the other way. Right? Is that right? See, I'm saying that if you have a smaller topology, okay, if you have two topologies, okay, I will erase this. Tau 1 is contained in tau 2. Okay? If a function f is continuous with respect to tau 1, okay, and suppose that means if x, that means what? That is if x lambda converges to x in tau 1, okay, then f of x lambda converges to f of x. Let's say f is complex value function, okay, f of x lambda converges to f of x. So now if x lambda, some y lambda some net converges to y, okay, in tau 2, then y lambda converges to y in tau 1. So this implies f of y lambda converges to f of y. So if it is continuous with respect to tau 1, it is continuous with respect to tau 2, right? So the argument is correct. You may get confused, so that's why I checked it. So prove that this is continuous with respect to weak star topology, but it is not continuous with respect to weak topology. So you have to use the idea. I'm giving you the idea also. You have to use the, see, if you remember, there is a, who gave the talk? It's uh, Shravar. So who gave the talk on, I don't know whether he's here. So it's on the dual of C0, dual of C0 is L1 and L1 star is L infinity. In the talk, there is something about something converges in using C0, but not in L infinity. Okay, so you have to use that fact. Okay? So the basis elements converges in C0, but they don't converge in L infinity. So if you remember, there is a, in the end there is a comment. If you use that, you will get that. Okay? So this is the assignment 2. Okay. Okay, so this will prove that this will prove that this assignment will imply that weak star topology is contained in weak topology, but it's a strict containment. Okay. Okay.
Sir,
Yeah. So
so I think the assignment problem should be the opposite. That
is that so?
Yeah, because weak is the larger topology, right? So if inverse image of every open set is weak star open, then since weak star is subset of weak, it will also be weak open.
Correct.
So it will be, that should be the
So
other
what
way.
is wrong with the statement, a convergent statement I said? So you are saying this could be correct. So if something satisfied f inverse lambda is contained in weak, yeah, that is what I said. If it is contained, so if it is continuous with respect to smaller topology, so it should be the other way. Okay. The negation should be the other way. Sorry, correct. Yeah, I proved that. So I just verified. Then I just verified that if it is continuous with respect to smaller topology, it is continuous with bigger topology. So here it is continuous with respect to a bigger topology, but not with respect to a smaller topology. Correct. So this is the right statement. So that is what I verified also. Okay. Okay. So this will imply that weak star topology is not contained in weak topology. Okay. Okay. Or you get you will get in that you will get a sequence which converges in weak star but not in weak. Right? No, it converges in weak star but not in weak. Okay. Yeah. So yeah, the convergence should be the other way. Something converges in weak star, but it's not converging in weak. So something is continuous in weak topology, but not in weak star. Correct. Okay. This is the right statement. Okay. Good. So now we want to prove one important theorem in about weak star topology, which is the Banach-Alaoglu theorem. The statement, the theorem is just the proof of the theorem is what usually one calls as tautology. It just immediately follows. It is just a statement. Writing it in a nice way. It is just the idea which matters. It's actually usually called Alaoglu theorem. Banach name is also there. Alaoglu, A-L-O-A, I believe. Alaoglu theorem. Okay, the theorem is the unit ball x star. Let's call it x star 1, which is equal to all phi in. So x is a Banach space. Okay. All phi in x star such that non phi is less than or equal to 1 is weak star compact. That's all. So before that, let me say a few things about compactness. Before that, so I have to say something I forgot. So this is a remark. Both weak and weak star topology or Hausdorff T2. That is, there exists, given any 2 points, there exists neighborhood, disjoint neighborhood. Okay? That is given x1, x2 in x, there exists neighborhood x1 in U, x2 in V, both open. Okay, that's what neighborhood means. Such that U intersection V is empty. So this follows because the linear functional x star separates points in x, and the evaluation function x contained in x double star separates points in x star. X star, correct. So that is, you want to produce a neighborhood. So I will show it for weak topology, and weak star topology is same. Okay, I mean weak star topology is much easier also. So given proof, given x1, x2 in x, there exists a phi in x star such that phi of x1 is not equal to phi of x2. Indeed, we can even say that there exists a, I mean, we have a phi which is not equal to 0 and phi of x1 minus x2 equal to norm x1 minus x2. I mean, by Hahn-Banach theorem. Okay, this is by Hahn-Banach theorem. Okay. Hahn-Banach theorem. So now you take epsilon equal to phi of x1 minus x2. We take the mod of that divided by 2. Or even less than that is enough. Okay. Now n, you take n x1, whatever I wrote it last time, phi epsilon, okay, and n x2 phi epsilon. This is, I mean, this is equal to all those x in x, such that phi of x1, phi of x minus phi of x1 is less than epsilon. Similarly, that are disjoint. Okay. U equal to this is equal to b. Okay. Then you take, similarly, you define b and verify that they are disjoint, of course, because epsilon is, this is epsilon is less than that, because of that. Okay. Similarly, you can do the same thing for weak star topology also. Given any phi1 and phi2, there will exist a x such that phi1x is not equal to phi2. That's what phi1 is not equal to phi2 means. So then you do the same thing. Just take the, I forgot to say that the neighborhood basis I want to write. So then, so this is another remark or something. Use this remark to prove that weak star topology is also Hausdorff. So the neighborhood basis or the basis, neighborhood basis base for weak star topology is given by n neighborhood x. No, it should be about phi. Okay, phi. This is comma. I mean, we produce. So if you remember the last class, we produce a neighborhood basis for the weak topology, which is given by point x and a linear function of phi1 up to phi n and an epsilon. So similarly, a neighborhood basis for weak star topology, here we have to consider a linear function. The point is linear functional, and the functions are evaluation function. So x1 up to xn and an epsilon. So this is equal to all those I and x star, that norm of phi of xi minus a of xi is less than epsilon, and I is less than n, and epsilon greater than 0. Epsilon is fixed here. So you vary the epsilon, you vary x1 up to xn, and you vary the phi, you will get the neighborhood basis for weak star topology. Okay, this is same thing. So please verify this. So this is same as, I mean, this is indeed easy. This is same as what we did for weak topology. Okay, so please ask me if you have any doubt with this. Okay, this. All those things vanished. How do you remove this? Do anybody know this? Okay. Good. But here also it has gone. Phi of xi is a of xi is less than norm of this is less than epsilon. So this gives the neighborhood basis for weak star topology. Okay. So okay. Now we want to prove that the unit ball of the dual space is compact in the weak star topology. So this is not usually this is not metrizable, but when the space is separable, when x star is separable, then it is metrizable. Okay, that also I think I will give it as an assignment. I will explicitly tell you what the metric is. So usually this is not metrizable. So if it is not metrizable, it need not be sequentially compact. Okay. If something is compact metric space, then it is sequentially compact. That is, if you have any sequence, then it has a convergent subsequence. So here, but you have to use net. Okay. So, or there are some other conditions. There are some universal net and all those things which I don't want to go through. So here compactness is different, but compactness certainly defined by, if you have any open cover, then there is a finite subcover. For any open cover, there is a finite subcover. That's the definition of compactness. Or you can define it through closed set. If you have a collection of closed subsets which has finite intersection property, that is, you take any finite subset, if their intersection is non-empty, then the intersection of the whole thing is non-empty. That is just the complement version of the open cover. If you have an open cover, if you have something covers that, that means you take the complements of all those open sets, then that the intersections will be empty. Okay. So if the intersection of the whole thing is empty, then there is a finite intersection, finite thing which has the empty intersection, finite amount of finite collection of closed sets. So the statement is, if all finite collection does not intersect to has a non-empty intersection, then the whole collection has a non-empty intersection. Okay, so it's a you can define it through either open cover or finite intersection property, but you cannot define through the convergence and all those things with sequences. You have to use next. Okay, so we want to prove the compactness in the topological sense, not in metric space sense. And this will be a metric space if X star is separable. Okay, so the proof, as I said, the proof is very direct. So to prove, I will use what is called Tikhonov's theorem. We will use, everybody knows Tikhonov's theorem. Everybody knows product topology and Tikhonov's theorem.
Yes, sir.
Okay, if someone, I mean, if there is someone who don't know this, then you tell me. Okay. Anyway, I will recall. So we use Tikhonov's theorem. It says the following: if you take Xi compact collection of compact topological spaces, then the direct product Xi is compact. You can take any, it need not be finite, it need not be countable, it can be uncountable. So if you take the direct product is compact with respect to product topology. So this is Tikhonov's theorem. So what is product topology? Product topology is the topology which is given by, you take, see, when you have the product, so what is this product to start with? Okay. This I in I Xi is all those functions from I to disjoint union Xi such that f of I is in Xi. Okay. Or if you take just one set, if you take the direct product of one single set, then that's going to be, suppose, I mean, that's what we will do in this. That's what we will do in this proof. If Xi equal to X for all I, then this is just, then we will denote it like this: X power I, which is equal to F from I to X. That's all. It is just a function from all functions from I to X. This is what the direct product is. Okay. So the product topology is which makes all those evaluation, which makes all those the coordinate function. You define Fi from Xi to C, not C, X, X, where F of any Xi. So it will be a tuple like this, possibly an uncountable tuple or something. So Fi of Xi is just Xi. So maybe you take Xj, this Xj, sorry, Xi. So it is the topology which the minimum topology which makes all these functions continuous. You can define it in the other way, which is given by, so this topology is given by all these kind of sets. You take ui1 cross ui2 cross uin, then you take the direct product with x itself everywhere. Okay? You take finite direct product of open sets ui1 up to uan, then you take the direct product with x everywhere, and that will give you a base for this topology. So, or you can forget about this. I mean, this is about open set, or you can say this topology is given by the product topology. You see, if you define a product topology, you can either declare all the open sets, or you can declare all the closed sets, or you can declare this is what convergence mean. This is what convergence means in the topology. So that's what I will define. So the product topology is given by sum fi lambda converges to f lambda in the product topology if fi is a, I have to write it as a tuple, no? So fi I in I. So f there is no lambda here. If fi lambda converges to fi for all, correct? That's all. Coordinate wise convergence. Okay. So some tuple converges to some other tuple, some net of tuple converges to some tuple if the convergence is coordinate wise. That's what the product topology means. Anyway, so the Tikhonov theorem says that if we have a collection of yeah, say
Sir,
hmm?
I'm a bit confused. Like, are you saying that product topology is the same as the one generated by these functions being continuous?
Exactly, correct.
Uh, I mean,
Is there a
okay,
problem? You take, see, you have a collection of topological spaces, then you form the direct product. You can take
did
the
we prove that or
hmm?
no? I have to.
I didn't understand
Okay.
what you mean.
Yeah.
Hmm.
Nothing. I was okay. I had to. Maybe I just have to think about it. Maybe after.
Yeah.
Yeah.
What
That's
is there to think about? It is just you take a collection of topological spaces, some collection, possibly an uncountable collection, a finite collection, or countable collection. Then the product topology is the topology given by the functions, the evaluation. I mean the coordinate evaluation functions. Okay, you take the coordinate projections.
Oh. Oh. Okay. Fine. Yeah. Yeah. Yeah.
Coordinate.
Yeah. Yeah.
So which is same as saying I mean, if you have a collection of functions, the topology given by is determined by the convergence. Something x lambda converges x if and only f of x lambda converges to f of x. Here the functions are the coordinate projections. So something converges to something if and only if the coordinate there is a coordinate wise convergence. That's all. That's nothing else.
And how is this related to weak topology or weak star topology?
No, it's not. This is a general statement.
Oh.
It's
Okay. Fine.
with topology or something. I am defining Tikhonov theorem. So this is this is the product topology. If you have a collection of something, then there is this product topology. Then the Tikhonov theorem says that these are all I assume that you know already. If you don't know, I have to go through all these things. Okay, I'm just recalling these things. That's why I'm not writing it in a very clear way. These are all. This is done in any topology course. Okay. So
Yeah.
if you haven't attended topology, you should tell me. This is
Yes, sir. It's fine.
so
Yeah.
this
I
is
just got confused.
yeah. This is product topology. Tikhonov's theorem says that if you have any collection of compact topological spaces, then the product, I mean, then the direct product of all those topological spaces is also compact. That's all. Okay. So this is we use Tikhonov's theorem. This is Tikhonov's theorem. Here to here. Let me write Tikhonov's theorem. Okay. Tikhonov's theorem says that if you have a two topological spaces, I and I, collection of compact topological spaces, okay, then I and I, xi is compact. I think I wrote the whole thing I did there with respect to product topology. That's all. It's a very strong statement, a very nice statement. I mean, this is not just about finite product or countable product. Even see, there may be some properties satisfied by all the topological spaces. But if you take even a countable direct product, finite product, it will hold. But finite countable direct product, it will not hold. But compactness, even if you take infinite product or uncountable product, then the product topology, the compactness is preserved. But you have to use the product topology. Okay? I don't know. What is this? Okay, so we are going to use this Tikhonov's theorem. So what we are going to do is, so this is the relation to weak star topology. Our theorem is Banach-Alaglu theorem. So I just recalled the topological preliminaries. We want to prove the theorem, Banach-Alaglu theorem, which says that if we have a Banach space X and the unit ball in the dual, the unit ball of the dual is compact in the weak star topology. That's what we want to do. Okay, proof of Banach-Alaglu theorem. Banach-Alaglu. So we want to prove that the unit ball is compact in the weak star topology. Unit ball of the dual space x1 star, x star is compact in the weak star topology. As I said, when you use the Tikhonov theorem, it's just the way of writing it. Then it follows immediately. Well, not very immediately. We have to verify some. We just have to write it down. Okay, so what we do is the following. If we have any closed subset of a compact set, that's compact. Okay, so that fact we are going to use. So we want to define the following. Define a F from, so X is Banach space, X is the Banach space. Banach space, X star is a dual space. Then you are defining the X star, the unit ball. This is unit ball, okay? F from X1 star to D closure power X1. Maybe I'll write it again. So it looks complicated, but there is, whatever, came back again, whatever here is. So let's define all those things. X is a Banach space. Let X1 equal to all X in X, the norm X less than or equal to 1. I mean, I'm just taking the closed ball. Take the closed ball. I think it does. Yeah, I should take the closed ball. And X star 1 is all those phi in X star. Norm phi is less than or equal to 1. Okay. Then I want to prove this X star 1, the unit ball in X star is compact. That's weak star compact. That's what I want to prove. So I define the following. F from X star 1 to D, I will define what is D. D is just the complex disk. To take the closed disk, power X1. Okay. There is no bracket there. X1. So where D equal to D closure equal to all this Z in complex number, mod Z is less than or equal to 1. Okay, you take the closed disk, all Z such that mod Z less than or equal to 1. Then you take the direct product of the, so which is compact. Okay, this is compact. Okay. You take the direct product with f of x, I mean x1. That is, this is equal to all f from D, f from x1 to D. F from x1 to D closure. Okay. All those functions from D closure. That's all. And this space is compact. Okay. With respect to product topology, of course. I mean, you can take a different topology. It's not compact with any topology. With respect to product topology. Okay, by Tikhonov theorem. So we have defined a map F from the unit ball of the dual space to this product space. So this space is compact with respect to the product topology. Now we just have to prove that this map is 1, 1 and it is continuous. Okay. So then it will follow that it's the range is, I mean, it is the, then this X star 1 is homeomorphic to its range. And we just have to prove the range is closed in that. Then it will be compact. So that's what we have. So the first claim is, claim 1 is F is 1 1 continuous. 1 1 and continuous. Okay. Okay. Once claim 1 is proved, if claim 1 is proved,
What is here?
what is?
Capital F.
I just defined here, no?
No, you didn't give the map.
Oh, I didn't define them. Okay, good. Sorry. That's it. So where shall I write it? Then that will go. Anyway, I will erase this. The map is just it's just the evaluation map. It's just the restriction. Okay. So f of any phi equal to phi. So it is just the phi restricted to x1. That's all. It is just the same map. So you have a linear functional phi. Okay, you just restrict that map to phi of x1. Then, oh my. Then, yeah. Then we know that phi is in, I mean, since phi is in x star 1, norm of mod of phi of x is less than or equal to, and x is in x1 equal to less than 1. Okay. So this is a function in, D closure x1. Right? You just take a functional phi, then f of phi is just this restriction to unit ball, which is a function from the unit ball taking values in this, because mod of phi of x is less than or equal to 1. Okay. Is it clear? Is it fine?
Yes, sir.
Okay. There is really nothing. I'm just taking a phi and then restricting to that something. Okay. That's all. So now we have to verify that this phi is continuous. So this is well defined. The map is well defined. This means that phi is f is well defined. Okay. It is indeed in that in the topological space we want to verify. Then you want to verify that f is 1 1. It all follows immediately. F is 1 1. So f is 1 1. So I was saying something. So let us go to the consequence of claim 1 later. Let us just verify this. F is 1 1. So that is the claim. The claim say, I remove the claim, is it? Okay, I will write the claim again. So we have defined a map F from the unit ball of the dual space to the topological space, the product space of D with respect to x1. Okay. We have verified it just as the restriction. The claim 1 is F is 1 1 and continuous. Okay, continuous with respect to weak star topology, continuous with respect to weak star topology, weak star topology. Okay. So F is 1 1 is clear. If f of phi1 equal to f of phi2, that means phi1 restricted to x1 equal to phi2 restricted to x2. But then it's a linear functional. If the restriction is same on the unit ball, then its restriction on something else will be, I mean, it's clear, no? This means phi1 of x by norm x equal to phi2 of x by norm x for all x. This implies phi1x equal to phi2x for all x. That is phi1 equal to phi2. So this implies f is 1 1. Okay. So f is 1 1 is clear. F is continuous. I mean, it is just direct verification. There is really nothing. That's what I'm saying. Okay. F is continuous. You want to verify with respect to weak star topology. So if phi lambda converges to phi in weak star topology, that is phi lambda x converges to phi of x for all x in x. That's what the definition of weak star topology. Okay. So that will imply that phi lambda, I mean, this is just this imply that f of phi lambda, okay, f of phi lambda at x, right? F of phi lambda x is equal to phi lambda of x. Okay, this converges to f of phi at x for all x in x1. Okay, that's what it means. This is equal to this, precisely equal to this. Okay, if the convergence in this is equal to this, so this implies f of phi lambda converges to f of phi in product topology. Correct? I mean, I'm just saying that everything follows. This is just the definition. You are just writing it in a different form, but it's all follows from the definition. Okay. So f is 1 and f is continuous in the product topology. So the claim 1 is proved. Okay. So claim 1 implies the following. Implies f of, so the map is defined on the unit ball of x star is f is homeomorphic to its image. I mean, it is continuous and it is 1 so it is homeomorphic to its image, which is f of min. X1 star is homeomorphic, but not this. X1 star is homeomorphic to its image. This is the image. F of X star. Okay. So the unit ball is homeomorphic to this. So to prove theorem, enough to prove f of that x star 1 is closed.
Sir,
Yeah.
so why will it be homeomorphic? We only get continuous bijection, right?
Homeomorphic to his image, not the homeomorphic to the whole thing.
Yeah, but I mean, continuous bijection need not be a homeomorphic, right? Homeomorphism, right?
What do you mean by that? I'm saying it is a closed set. What do you mean by continuous bijection? Is the inverse image? But okay, but we will prove it's compact. No, it's continued on that. I mean, if we prove that it's a closed set, then it is continuous. Okay?
Yeah, I mean, we need to prove compactness first to conclude that this map is a homeomorphism.
No, that is compactness. No. Okay, sorry. Its inverse is also continuous. Okay, good point. Thank you. So if it is 1 and continuous with, maybe I will do this following. Good, thank you. You are right. So f is 1 and it's the same thing. It's just the definition. And phi lambda converges to phi in weak star topology is equivalent to f of phi lambda converges to f of phi in product topology. Okay, these two convergences are just same. Good, thank you. Okay, so that just follows because of this. This is equivalent to that. So I just have to verify the other thing. So let me not write it. If phi lambda converges to phi in weak topology, that's what this means. Then this is equivalent to that. It's the same statement because they are equal. It's the same statement. So kind 1 implies that, yeah, now it's clear.
Yes, sir.
Yeah, now it's fine. Okay, it's just the both are same. Okay, so now this implies that x1 star is homeomorphic to its image. Okay, now it's all we have to prove that the f of x. We haven't used any idea till now. We just wrote down something. We just wrote down the duals, the ball in a different form, and then we just verified that this is same as that. Okay, so now it is enough to prove that this is closed in whatever that dx. Okay, this is just closed in there. Okay, so to prove this, we verify the following. So we make the another claim, claim 2. So here we need some claim, but that's also easy. The claim is given a function f from given a continuous function, maybe you do in a continuous function. Given a function, okay, let f from x x1 to c. Okay, given a function, there exists a phi in x star such that phi restricted to x1 equal to f if and only if and only if the first condition given a function from x1 to d, I mean d closure, there exists a phi in x star, there exists a phi in x star 1 such that phi restricted to x1 is f. Okay, if and only if the f already satisfies the first condition, if and only if for all alpha, beta, xy in alpha, beta in complex number, xy in x1, and alpha x plus beta y. Also, this also satisfies in x1. Okay, f of alpha x plus beta y equal to alpha times f of x plus beta times f of y. I mean, the linearity is satisfied for in the restricted sense. It is enough to have that. See, we want to have we have a function f from the unit ball to close this, and that function is given by a linear functional in the unit ball. If and only if the linearity is satisfied, maybe this is the only condition. Let me see whether I need one more condition. The linearity is satisfied in this restricted sense. Okay? So this one way is clear, of course. If there exists a phi satisfying that, then f will satisfy this. This is from the linearity, it will satisfy that. So we have to prove only this way. Okay? Only this way need to be proven. Okay. So how do you do that? So how do you define? If you have any f, then you have to define. So given any f from x1 to d closure, satisfying that condition, satisfying this condition, let us call it star. Okay, satisfying star. Define phi of x equal to there is only one way of defining f of x by norm x times norm x, right? X not equal to 0. For x equal to 0, f of 0 has to be 0. Because that will follow from the linearity anyway. Okay? So for phi of x for x not equal to 0, we have to define, and when something is not in the unit ball, we have to define. So for that, it satisfies this. It is defined by this. Then we have to verify that this phi is actually linear. Okay. So Phi continuous. We need it continuous. Okay. And phi will also be continuous when we define it like this. So we only have to verify. We have to verify the linearity of this. Then phi is linear. Okay. Okay. So to verify linearity, we have to verify the following: phi let lambda mu in C and x1 x2. We want to verify linearity in general. Okay, we have a linearity on the ball, but we want to verify the linearity in general. Okay? Then phi of lambda x1 plus mu x2 is of course equal to. I mean, the zero things you just don't. You can please verify that that satisfies anyway. I mean, by the same way you can verify for the other cases also. This is equal to norm of lambda x1 plus mu x2 t of lambda x1 plus mu x2 divided by norm of lambda x1 plus mu x2, right? That is how it is defined. Okay. Now we want to verify this is same as this. Sorry, this is f. Now on the other hand, we have to verify this is same as phi of lambda times phi of x1 plus mu times phi of x2, which is equal to lambda times norm x1 times phi of f. This is f. F of x1 by norm x1 plus mu times norm x2 f of x2 times norm x2. Okay. Now I make another norm of, I just multiply by this norm of alpha, lambda norm of lambda x1 plus mu x2. Just put it out and then lambda by norm of lambda x1 plus mu x2. You just multiply and divide by this times norm x1 times f of x1 by norm x1 plus mu by the same thing lambda x1 plus mu x2 x2 by norm x2. Now we know that this constant, whatever we have here, lambda norm x1, that is, I mean, that satisfies the it is just clear. Norm of norm x1. You take this as alpha equal to this. Take alpha equal to lambda norm x1 by lambda x1 plus mu x2 and beta equal to similarly. Okay, similarly the other one. Then this alpha beta will satisfy this condition. Okay, we assume that f satisfies this condition. Linearity is satisfied in the this restricted sense. Then you can take the whole thing inside. So this implies this is equal to lambda x1 plus mu x2. Okay, this thing is equal to times. You can take it inside. Then the x1 will cancel. Okay. The x1 will cancel. If you take it inside this, the whole thing, then x1 will cancel and you will only get this lambda phi f of lambda by lambda x1 plus mu x2. Okay? And you can take, I mean, by linearity, this is equal to lambda x1 plus mu x2. So which is same as phi of lambda x1 plus mu x2. That's what we have. See, we have phi of lambda x1 plus mu x2 looks like this. Okay, and that is what we have got for this. I mean, this is an easy verification you should do. Okay, this is okay. Maybe I'm. Is this fine? Someone say yes, I will proceed. Otherwise, I will go through it again. There is really nothing. We have a f which satisfies linearity in the restricted sets. Okay. Then we define using the f which satisfies linearity in the restricted zone. Then we define a functional f phi using this f by this condition. Okay. By this condition here. Okay. Here we define it like this. So then you verify the linearity of the phi using that. Okay, if you don't understand, you look at it again. It will be easy. It's an easy exercise. Okay. So we have to. So all we have to prove is now we have to. So this is the claim. This is the claim 3. So claim 2 is proved. We have to prove the claim 3. Claim 3 is f of that x star 1 is nothing but intersection of all alpha, beta, xy with alpha, beta, in C, xy in x1, okay, such that this set, all those phi in, not all those phi, all those f in closure x1, which is the space we are considering, okay, such that f of alpha x plus beta y equal to such that alpha x plus beta y is in x1. This is equal to alpha f of x plus beta. This is clear. By the claim 2, this is clear. Claim 2 says that, what does claim 2 says? Claim 2 says that if you have any function like this, then that function is given by a linear function. It is just the restriction of a linear functional, continuous linear functional, if and only if f satisfies this condition. Okay. So it follows that the f of x1 star, which is just, I mean, the image of that f is all those f which satisfies this condition, this linearity condition. But then this set is closed. I mean, this is for a fixed, you call this set as, call this set, this is equal to intersection of all those k, alpha, beta, xy. Okay? And k, alpha, beta, xy is closed. I mean, they are all continuous functions and there is an equality sign and you can see that that's a closed set. Okay? Such a set is closed. If some sequence converges, then the image also will satisfy. Some f lambda converges to f, then the all f lambda satisfies this thing, this equation, then the limit will also satisfy this equation because of the equality. So this set is closed, and you are taking arbitrary intersection of closed set, so that is also closed. Okay, so theorem is proved. Yeah. So if you have any problem, you tell me. I will go through it. And I cannot write anymore. As you can see that there is really nothing in this proof. You just write it in a different form and you verify everything satisfies the actual conditions. Anyway, this proof I have just taken from Sundar's book, but there are not, all the details are not there. I have just verified all the details for you. You have to verify otherwise detail, but you can look at the notes. Okay. So this is the proof of Banach-Alaoglu theorem. So I want to stop if you don't have any questions.
Okay, sir.
Any questions?
No. Yeah, this is.
Say it loud.
I mean, yeah, this is fine.
This is fine. Okay, so this is very easy. If you have any doubt, you go through the proof again. Okay. Okay. Goodbye.